one and the admin.
Can you see the screen now? PowerPoint presentation.
Yes, sir.
Yes, sir.
Yes, sir.
So we were discussing about the equation of motion and the different components which are involved in the structural dynamics. So initially we are starting with the single degree of freedom system and how to formulate the equation of the motion. The important point is that you know that these are second order differential equations. So we have to compute the mass value, stiffness value and the dampness value with the acceleration and similarly with the displacement and velocity respectively. So what are the different components of for making the equation of the motion? Basically, a single degree of freedom system can well explain the different civil engineering structures and also can be represented by spring mass system, a system whose dynamic response can be described by specifying displacement along only one direction is basically called as a single degree of freedom system. So we are considering the displacement in one direction for single degree of freedom system. And true engineering system or multi-degree of freedom system, actually there are more than one degrees of freedoms are present at every story, but this is we are doing it as idealization that we are making it as a single degree of freedom for solving our problem. So you can say that we are considering the displacement at top, mass at top, the total mass, and also we are considering the beam as a rigid beam so that there is no internal deflection in the beam in horizontal direction because beam is rigid enough in the horizontal direction. But stiffness of the columns will be computed. So in this way, we can represent the single degree of freedom system. For many engineering systems, the single degree of freedom idealization is satisfactory. We can say that the single degree of freedom system is fine for the many system. Dynamic analysis of single degree of freedom system is simple and can be extended to more complex multi-degree of freedom system. Initially, you start with the single degree of freedom system, and if you learn about the free vibrations and the four vibrations and the harmonic vibrations of the single degree of freedom system, then you can extend your work to the multi-degree of freedom system. So, a single degree of freedom system here in the figure, it can be represented, and you can also see that a system can be represented by three components. Here is the mass which is considered at the lump mass and the stiffness which is for all the columns, the sum of the stiffness is taken out, and the third one is the dampness. So these three values are basically there and which can be used to represent the single degree of freedom system. If you want to show the system by spring mass system, it is comprised of the dampness plus the stiffness plus the mass, and the u is basically the total displacement from the center and p is the applied load. So these are the different components, and basically the stiffness linked with the material property and the dampness linked with the energy dissipation, that is due to the friction between the sports and the ability of the body to dissipate the energy during the seismic vibrations. And the third one, that is a mass, that is a inertia. The mass represents the inertia of the systems. So components of the dynamic systems are the mass resulting in the inertia force, stiffness which is resulting in a spring force, and energy dissipating mechanism which is resulting in the damping force. These are the three basically components, and external exciting force. These four components represent a dynamic system. Mass, that is resulting in inertial force, and stiffness, that is resulting in a spring force Fs, and energy dissipating mechanism, that is resulting in a damping force. From direct equilibrium, as last time the different principles were explained, from the direct equilibrium, from the D'Alembert principle, we can write that the sum of all the forces, inertial plus dampness plus spring, is equal to the external exciting force. So external exciting force is basically resisted by the three components: the inertial components, the damping components, and the stiffness component. You know that the Fi, the inertia, is equal to, this is due to the mass. So when there is a changing acceleration, because force is changing with respect to the time, so definitely when the displacement is also changing, so displacement can be represented as the du over dt. Displacement is also changing, and the first displacement, rate of change of displacement, is velocity u dot, and the rate of change of the velocity is the acceleration. So with the mass there is acceleration ma, plus with the damping force there is a velocity only, the damping coefficient and the velocity, and with the stiffness force there is a k value and the stiffness and the displacement. So in this way you can represent the mass spring system. If you want to draw the free body diagram of this system, you know that the PT is applied load, is shown in this direction. Fi is the inertial force, and Fd is the damping force, and S is the spring force. Inertia force, the force produced in a dynamic system due to the translation acceleration of the mass, that is called as inertial force, and which is equal to m into u double dot and ma, the force produced due to the rotational acceleration. Sometimes there is the two force, because when you are moving the body in the lateral directions, that is the inertial force and translation force. But when you are rotating the body, when you are applying some movement, then it is equal to I times theta. I is the mass movement of inertia, and theta is the ground acceleration, rotational acceleration. So that's why if the body is moving in the linear direction, you will take it Fi as mu, but when the body is moving in the circular direction, then you will take it as a mi equal to I theta. Similarly, the spring forces, internal forces induced in a body undergoing deformation. Spring force basically exists both in static and dynamic systems. And for elastic system, the spring force is directly proportional to the deformation produced and is equal to the stiffness times the deformation. You know that the stiffness force is basically the force required to produce the unit deformation is stiffness. So it means that the stiffness force, the spring force, is equal to stiffness times displacement. So when you applied any system for elastic system, the total displacement multiplied by the stiffness gives you the force. However, for inelastic system, the spring force is dependent on both displacement as well as on the velocity. For inelastic system, you also need the other parameters. Question about the damping. The damping force basically is a process by which a free vibration steadily diminishes and in amplitude due to the dissipation of energy, and the corresponding force is called damping force. There are many energy dissipation mechanism, and different devices are used to dissipate the energy. So for example, heating of the material due to internal friction, opening and closing of the micro cracking, friction between the structural and the non-structural components, connections, external devices. These are all basically used as a dissipating mechanism forces. Heating of the material, because the energy goes to the heating of the systems, closing of the cracks, opening and closing, and friction between the structural and the non-structural components. Similarly, the connections and external devices. So all are these basically the mechanism for the dissipation of energy. Equivalent viscous damping force can be represented by C time U. Damping force can be represented by velocity into the damping coefficient. It is just like a piston which is moving, and how much is the velocity of that, and you can see the dampiness of every piston is the property that depends upon the friction between the piston and the basically the component where the piston is moving. So basically it is not difficult to make the equation of the motion, and you guys are required to develop the equation of the motion for the different systems, and you can apply in the real structures that how to write down the equation of the motion for any structure. For example, a dynamic system may be a system with localized mass and localized stiffness, system with distributed mass and localized stiffness, system with localized mass and distributed stiffness, and system with the distributed mass and the distributed stiffness. There are the different systems basically which can represent the dynamics. One is the localized mass and localized stiffness, distributed mass and localized stiffness, localized mass and distributed stiffness, and distributed mass and the distributed stiffness. So how you can basically, normally we are considering it as a system with localized mass and the localized stiffness, because we are transferring the mass at one level, story level, all the mass. You can include the mass of the beam and the some part of the columns. We are utilizing the mass at that level, and similarly the stiffness we are considering for the columns, and we are not taking the deformation, internal deformation in the beam. So stiffness that is based on the rigid beam is computed. So if these are the three components Fi, Fd and Fs for the equation of the motion, then you can write the equation of the motion as mu cu plus ku is equal to pt, and this is the representation of the equation of the motion. Now you have to, let's say you want to write the equation of the motion for the different systems, so you should be able to write down the equation of the motion for the different systems. For example, an overhead tank which is free at the top, let's say the free body is like the mass is fixed at top, and actually the mass is considered at the top and it is moving in the lateral direction. Now how to write down the equation of the motion? The mass is considered lumped at the top. If the top end is considered free and the bottom as the fixed, what will be the K value? The K you should know for the different structural components. So it is 3ei over L cube if it is free at the top. If it is fixed, or then it is different, 12ei over L cube, and depending upon the end conditions, actually the stiffness also changes. So you know the mass in the dynamics is written in terms of the W over G, because we have to involve the G value in the mass. So stiffness is in, let's say, Newton per second or pound, Newton per millimeter or pound per inches. The mass should be in kilonewton second square per meter or pound second square per inch. So in this way the mass can be written. So putting the values of the W over G and stiffness 3I over L cube, you can write down the equation of the motion. With the acceleration, the component W over G is involved, and with the displacement there is no damping in this case, because you can see the spring mass system for this case, because damping was not given. So this will become the spring mass system for this overhead tank. So you should be able to basically represent your structural system using the spring mass system. In this way you can write down the equation of the motion. Now this becomes the second order differential equation, and you have to solve it by using some advanced methods. And you should be able to represent the different systems using the spring. For example, if the stiffness is summing up, then the springs will be in parallel. When the stiffness is not summing up, but one displacement is affecting the other displacement, then the stiffness cannot be summed. In this case, the displacement is same. U is the one value, because spring is a elastic material. So when you applied some load here, equal displacement is generated at this point and at this point. Therefore, the force that is developed in the spring 1 is K1 into U, spring 2 is K2 into U. So what will be the total force, the spring force that will be developed? Is sum of that, because the equivalent stiffness is K1 plus K2. This is the equivalent stiffness, and multiplied by the U value. Multiplied by the U value, because this is a displacement. So that will give you the spring force. What is the effective stiffness? Ke, that is the spring force divided by the displacement. So K1 plus K2, the equivalent stiffness is basically K1 plus K2. That is the effective stiffness. And the equation of the motion will be equal to mu plus Ke into u. So stiffness in the one spring is Fs over u1 and stiffness in the other spring is Fs over u2, and in this way you can determine the equation of the motion by computing the equivalent stiffness. Now you have to think about the springs in series. What changes will occur when the springs are in series? When the stiffness of the one component and the displacement of the one component is affecting the other component beyond, it means that the total displacement u is dependent on the displacement of the individual spring. The reason is that these are in the series. So displacement of this spring is, let's say, u2. Displacement of this spring is u1. So total displacement is u1 plus u2. Therefore, you can say that the force in the each spring is equal to Fs. It means that the force in the one spring stiffness is K1 into u1 and force in the other spring is K2 into u2. This means that when you are computing the u1, so u1 is Fs over K1, u2 is Fs over K2, and total u is Fs over K equivalent. So this implies that because Fs is the constant force which is acting at the end, so equivalent stiffness in this case will be not the sum of that but sum of the inverse of the stiffnesses. 1 over Ke is equal to 1 over K1 plus 1 over K2. In this way, you can compute the equivalent stiffness. So what will be the equivalent stiffness? This will be the equivalent stiffness. So the equation of the motion will be the force is applied at the end, Pt is equal to mu. That is not linked with the stiffness but mass term acceleration and plus Ke into u. So in this way you can write down and solve the different problems and convert the real structure problem into a spring mass system and develop different relationship for the different structural system. Next is that you should try to work on the different systems, as I am saying that simulation of the problem with spring mass system. Let's say there are two components where the stiffness is parallel, but then the one component is attached which is in series with these two components. So you have to make it simple and determine the equivalent stiffness. How to make it simple? that these parallel, basically the springs, these will convert the stiffness to the equivalent stiffness because these are parallel. So equivalent stiffness is K1 plus K2. Now the sum of the K1 and K2 will be in the line with the K3. K1 and K2, the sum of this will be in line with the K3. So it means that K1 plus K2 and K3 are in series, but K1 and K2 in parallel. First solve the K1 and K2. So this will, then this is in series with the K3. Then you have to solve it. So try working on it, that what will be the KE value for this case. You know what will be the KE value for this case? Mute your mic, please. So what is the KE value for this case is 1 over K1 plus K2 plus 1 over K3. That is equal to 1 over KE. So in this way you can determine the equivalent stiffness and solve the problems. Similarly, the different kinds of the beams are there. Any beam system can be represented. Let's say there is some force you can draw for the different beams. Let's say this is a beam, and this is the beam. So how can you represent the stiffness of this beam? Definitely the displacement in the center. Any beam can be represented by this spring mass system, where spring is the stiffness of that structural component, W is the weight that is acting in the middle or wherever, where you are determining the U. So W is in line with the U value. So you can actually determine the stiffness of the different beams components using this analogy that make it as a spring mass system, any beam. Let's say I have shown here the three cases that the beam is simply supported with a cantilever beam and beam is a clamp beam. There are the three cases, and you can basically determine the stiffness. How? First, you should know that due to the effect of that loading, let's say there is a cantilever beam and the load is acting at this point, Fs, then what will be the displacement at this end? What is the U value? The load is acting at the center of the simply supported beam. What is the U value here? The load is acting at the center of the fixed ended beam. What is the U value? So these things are already known. I mean, from the deflection problem, deflection chapter, you can see that the central deflection for the point load is Fs L cube over 48 EI for the simply supported beam. For the cantilever beam, it is PL cube over 3 EI. For the fixed ended beam, it is PL cube over 192 EI. So from that, if you have all the stiffnesses values, U values, so you know that the stiffness is equal to inverse of the P over Fs over del U. Stiffness is Fs over U. So you can simply put down the values and the stiffness can be computed. Because stiffness for the case for the simply supported beam is 48 EI over L cube. Stiffness for the cantilever beam is 3 EI over L cube. And stiffness for the clamp beam will be 192 EI over L cube. So what will be the equation of the motion for the different beams? For simply supported beam, it is m into u dot dot plus k into k K into U, where K is the value it's written. Similarly, for the cantilever beam, the equation is same, only the K value is changing. So if you know the mass, you know the stiffness, you can write down the equation of the motion for this system. So these were the system where the load was acting. I mean, the load is acting in the middle of the beam, the W, the weight is acting, or the force is acting. In addition to W, maybe not only the force is also acting, plus there is a weight also. So it depends that there is a force or force also acting, or only there is a weight. And if the load is not present, the equation of the motion will be equal to 0. But if the load is present, the equation of the motion will not be equal to 0. So sum of all the components is equal to Pt. In one case, it is equal to the Pt like this. And sometime if the Pt is 0, then you can say that, like in this case, there was no force. In this case, there was no force acting on the waterhead tank. So there is a Pt is equal to 0 value. But if the load is acting at the end, the Fs is acting here, so therefore it is not equal to 0. Write down the equation for the different power systems. This was about translation movement in the one direction due to the lateral force, the effect on the structural system due to the effect of the lateral force, and for the single degree of freedom system, making the equation of the motion. Now the next one is the developing the equation of the motion for the system which is the earthquake excitation. What will be the happen to the system which is under the earthquake excitation? So there is no force on the top. There is no force on the top, but only the ground acceleration at the bottom, ground displacement. Because due to the earthquake load, what happens? The ground displacement is there. So in that case, there will be two components actually, because you know that the total will change. Total displacement will not only be the ground, and definitely the ground acceleration or the ground movement is just displacing the building at the bottom. So that is the UG. But at the top, the building is total displacement is UT. Top UT is, and in addition, so when the structure is subjected to the ground motion, there are two kinds of displacements. One is the UT, total displacement is UT into T, the total one, and that you have to take the sum of the UT, that is due to the structural system, structural properties, and second one definitely because the building is already, this was the original position of the building, this was the original location, and the building is displaced equal to the UG. So when the building is already displaced, you have to add that component to the displacement. Now the total displacement is equal to the UG into T. This will affect the inertial force also. This will affect the inertial force, because in that case, you know that there is no force. Force is 0. And this will be the sum of the force. But inertial force now, because the total displacement will acceleration, total acceleration. That when you put down the values m ut and ut is equal to sum of the acceleration of the ground plus acceleration in the body system. So one acceleration is in the system and one acceleration in the ground. But because these are in the same direction, so write down the equation become mu plus cu plus ku plus mug is equal to 0. But when mug is brought to the right hand side, it is converted to the minus mug. So you can write down the equation for the ground vibration or the ground movement as this one, because I told you that acceleration is changing, whereas the other forces, with the other forces it is just u and u, because stiffness is not depending upon the ground acceleration and dampness is not depending on the ground, but the acceleration is basically the depending upon the ground acceleration. Therefore, the total acceleration is sum of the ground acceleration for the body acceleration. So you put down the values where mass into u plus mass into u times g, the ground acceleration. So when you put the ground acceleration on the right hand side, because actually all are in one direction. So you sum it and then you can write down the equation in this way. It means that when the system is subjected to the earthquake excitation, the right MUGT is coming, and that is actually force. It means that the force is not zero on the. You can say that it is a P effective into MUGT. So you can declare it as a force basically when the system is subjected to the ground acceleration. This is the case when the structure is subjected to the ground motion. Please mute your microphone. Clear? Is that clear?
Yes, sir.
Yes, sir.
Yes, sir.
So I can represent a system, a system which was a normal building but subjected to the ground acceleration. It is basically the same case when I remove the ground acceleration and apply a force at top. The force amount is equal to mass times acceleration. So this is the same case. That's why we analyze like this case, because ground acceleration into mass is the effective force acting at the top of the building when the earthquake is basically hitting the building at the bottom. You can show it like that. Therefore, this is the equation of the motion for the case when the building is subjected to the ground motion. Ground motion is of two types now. The first case that I discussed now, ट्रांसलेशन, इसको आप ट्रांसलेशन कहेंगे क्योंकि ग्राउंड मोशन इज बेसिकली इन वन डायरेक्शन. समटाइम देयर इज अ मूवमेंट, समटाइम देयर इज अ ground rotation, base rotation also. So the next case I am discussing about the base rotation. This case was about the ground translation, and the next case will be the ground rotation. Now another system which is not subjected to the ground displacement but base rotation. You know that earthquake sometimes rotate the base of the building. Sometimes it just move in the translatory direction, one direction, it is a translation. और दूसरा इसको हम कहेंगे a base rotation. So when you have a, इसको हम फिर theta g कहेंगे क्योंकि ground rotation हुई है ना, तो this is a theta g. So initially the body was straight, totally straight. Theta g occurs and this rotate up our system to a new position. But you know that when a body is rotated and it is a stiff system, it will start. Additional displacement is generated as a u. The total displacement will become ut. Ut अब किसके equal होगा? Ut will be equal to the sum of the displacement produced by the stiffness body system plus the ground So you can compute by the formula L is equal to, because theta of the earthquake is taken is in the radian, so L is equal to R theta. So you can say that if H is the height of the building, this first part of the displacement is equal to H theta T, and this is then, and you can mark it because these are very small values, so you can assume that is a radian L is equal to R theta, and the formula can be used. So it means that the displacement produced by the ground rotation, this is not the rotation actually, this is the displacement. So angle is converted to the displacement. So this displacement plus the displacement due to the motion that is produced in the structural system. So sum of that is the total displacement. And what happened that this displacement will only affect the inertia again. The inertial force will be now MUT, and UT is, you know, that UT is M into acceleration, and this will be the sum of the U, the ground displacement. So you will take the sum of that both system. So again, the system which is subjected to the ground or the base rotation, a system which is subjected to the ground or the base rotation, you can write that system as mu plus cu plus ku is equal to minus mh theta g, and this is basically the equivalent force, or you can represent the system in this form. If you say that there is no ground rotation, but you want to apply the loading, because for the second we are practically applying the loading at the top. So that rather than that, you can apply the P effective is equal to minus h theta g. So you can also apply this system. So left hand side system shown in the figure will be equivalent to this system. If the stationary base is, if the base is not moving, rotating, but you convert it to the stationary base. So this will have the same system, okay? So in this way, the ground acceleration is basically when there is a ground acceleration, the m into h theta g, or when the system is rotating, then the thing is different, as I told you. So you should be able to develop the equations for this system also, because the values of the mass is known, height is known, and the ground acceleration is known. So you can write down the equation of the motion for the system which is subjected to the ground rotation. Now some of the problem when a disk problem from your book. Because the previously case that we discussed was about the writing down the equation of the motion for the linear system when the linear translation is produced. But say when there is a rotation, displacement is in terms of rotations, not the linear movement, then how to write down the equation? And what changes occur? Because when the beam is a cantilever beam, you say, okay, the displacement is 3I, stiffness is 3I over L cube, and you can write down the equation. But whether the stiffness is used in case of the rotation, when the rotation is applied on any structure, let's say this is a disk where a rotational force is applied at the base, let's say, and this is rotated by the theta angle. Then how to write down the equation of the motion for this case? So in that case, the spring force or the force of the stiffness Fs will be not equal to kg. इस केस में आपने याद रखना है, the force will be equal to the mass moment of inertia into the rotation. So this is a mass moment of inertia, as I told you in the lecture last time, that when the body is rotating and you are computing the mass moment of inertia. For the circular disc, the mass moment of inertia basically can be represented as the moment of inertia about the centroid divided by the, this is basically r square over area, radius of gyration square over area. So you are doing that as that radius of gyration is computed, and from that you can compute the mass moment of inertia. So when you are computing the mass moment of inertia, you can basically, for the circular it is a mr square over 2. I can review that after this slide, that how to compute the mass moment of inertia for the different systems. So one thing is that you will write down the equation in terms of the mass moment of inertia. This is minus because the load was applied there and the angle is produced in this direction. That's why it is a negative. And Fs, right, the torque twist. Now we know that the force when any body is subjected to the movement, any body is subjected to the ground displacement or rotation, theta. What will be the torque twist relation that you studied in the mechanics of material? You know that it is equal to G into theta. Fs will be equal to GJL over theta. This is the relation. Torque twist relation is GJ over L into theta when any body is subjected to the some rotation. So it means that theta is the rotation. So GJ over L, this will give you the total force Fs. So J is the polar moment of inertia, that is 2 times the I. So J is equal to 2I, and you can determine that as pi d4 over 64 multiplied by the 2. So that comes to the pi d4 over 32. Now the equation of the motion in this case for the rotating disk will be I naught into theta. Spring force is I naught into theta, and plus J over L into theta, because Fs is equal to Gj over L. So that is you can sum the values, and one with theta is used with the this value can be obtained as a stiffness, and acceleration के साथ आप mass नहीं use करेंगे, you will use this with the basically the mass moment of area use करेंगे. When there is a rotation, तो क्या change आएगी? You will not use m into a, but you will use the mass moment of area into the acceleration due to the rotation. So the sum of that will give you the equation of the motion. Or you can put down the values, and so for this disk which is subjected to the rotation, rotational basically rotation at the base or rotation of the disk without any force, then itself you can say that it is equal to mr square over 2 into theta plus pi d4g. Putting down all the values, you can write down the equation in this form. So this is the case when your disk is subjected to the rotation. And previous equation of the motions were built when the disk is subjected, or any system is subjected to the linear movement. This was the case when the structure is subjected to the linear movement, and this is the case when the structure is subjected to the base rotation. So in this way you should be able to solve the different problems which are linked with the equation of the motion, and try working on it. about the mass moment of inertia in this lecture. The mass moment of area was for different cases like this one. For different shapes, the mass moment of inertia is written on this slide. You can determine the mass moment of inertia for the different cases. Because mass moment is equal to m into r square, actually, and r is the radius of gyration, which is ix over a. You can determine the mass moment of area when it is needed, when the system is subjected to the base rotation. So in this case also, it was chosen. If you have any question, ask. This is the first part of the lecture is over, and we will start the new topic. Do you have any questions from this part of the class?
No, sir.